At the center of a star that has been burning for 10 million years, something has gone quiet. Not the star itself. The star is still immense, still radiant, still holding billions of tons of hydrogen in its outer layers, still throwing light across the light years of dark space that surround it. The surface blazes, the upper layers churn with slow convective rolls wider than planets. From outside, from any distance, this star looks like a star in its fullness, a sun doing what suns do, ordinary in its violence, ordinary in its fire. But at the center, the fire has stopped. The innermost region of the star has been building toward this for a long time. Fusion does not stop at once across a whole star. It retreats, layer by layer, element by element, like a fire burning inward through a log. Hydrogen burns first in the core for millions of years. When the hydrogen at the center is spent, the core contracts under its own weight and grows hotter, and that heat ignites a shell of hydrogen burning around a helium center. The helium core, meanwhile, contracts further still until it too becomes hot enough to burn, fusing into carbon and oxygen. The carbon burns later, when conditions allow it, into neon and magnesium. The neon burns, and the oxygen burns, and the silicon burns, each stage shorter than the last, each stage hotter and faster, each stage leaving a new kind of ash in a new innermost shell, and pushing the burning outward into the layer above. If it were possible to stand outside this star and peel it like an onion, each layer would reveal a different fire burning at a different temperature in a different chemical language. Hydrogen near the surface, helium beneath it. Carbon, then neon, then oxygen, then silicon, each burning in a shell wrapped tightly around the one below. The whole structure is alive with fusion at every depth, a set of nested furnaces, each feeding the gravity that would otherwise crush them, except at the very center, where the last fire has gone out. The silicon burning in the deepest shell has been converting nuclei into iron and nickel for about a day. Iron sits at a peculiar position in the physics of atomic nuclei. For every element lighter than iron fusion releases energy. It is possible to combine two lighter nuclei and end up with something heavier that weighs in a precise and specific sense slightly less than the two parts combined, and that missing mass escapes as heat and light and outward pressure. This is the mechanism that has kept the star alive for 10 million years. Mass becoming energy, energy pushing outward, outward pressure holding the star's own gravity at bay. But iron breaks this economy. An iron nucleus is already bound as tightly as a nucleus can be. Fusing iron with anything, trying to push it toward any heavier element, does not release energy. It costs energy. The binding energy curve, climbing steadily from hydrogen through all the lighter elements, peaks precisely at iron and falls away on the other side. So iron does not burn. It accumulates. Each silicon burning shell consumes its fuel and adds more iron to the core below, a slow and steady deposit of the one substance in the universe that cannot be lit. The iron core sits inert at the star's center, dense and hot and still, growing heavier by the day, while every layer above it continues to burn. For a few centuries of the star's multi-million-year life, the iron core grows. It holds itself up by electron degeneracy, a quantum mechanical pressure arising from the fact that electrons resist being compressed into the same states, a resistance with nothing to do with temperature and everything to do with the behavior of matter at very small scales. This pressure is real. It holds the core stable for a time, but it has a limit. The limit is roughly 1.5 times the mass of the sun. Deep in the iron core, The electrons and the accumulated iron nuclei press against one another in a silence that grows slowly more extreme. The temperature exceeds 100 billion degrees by the end, but temperature no longer helps. The core is past the point where thermal pressure matters, past the point where fusion could start, even if there were anything left to burn. What holds the core up is entirely the quantum stubbornness of its electrons, and as more iron falls inward from the silicon burning shell above, that stubbornness is reaching its end. The core has no way to signal what is about to happen. There is no sound from the center of a star, no warning that propagates outward through the burning shells. The outer layers of the star, still fusing furiously in their own fires, have no way of knowing that the foundation beneath them is approaching the moment of its failure. Then the mass tips past the limit, and the core falls. The collapse happens in less than a second. That is the truest and the strangest thing about it. A volume larger than the Earth, containing more mass than the Sun, falls inward at roughly a quarter of the speed of light, tens of thousands of kilometers per second, and compresses itself to the size of a small city. The outer layers of the star, which are still burning, still fusing, still pushing outward in their normal way, have not yet had time to feel the collapse. Light takes 8 minutes to cross from the Sun to the Earth, but the distance from the iron core to the star's surface is nothing like that far. It is a fraction of a light second. The information about the collapse will arrive at the surface eventually, but for a fraction of a second, the star does not yet know its own center has gone. What happens inside the collapsing core is stranger than what is visible from outside. As the electrons and protons are pressed together under the force of the implosion, they combine. An electron and a proton meeting under sufficient pressure produce a neutron and a neutrino, a tiny, almost massless particle that interacts with matter only through the weak nuclear force and through gravity, which is to say it barely interacts at all. This process, repeated across the entire core in less than a second, converts the iron and nickel into a seething mass of neutrons and floods the collapsing interior with an almost unimaginable number of neutrinos. The neutrinos carry energy, not a little energy, a quantity of energy so large it needs careful consideration to hold without losing the sense of it. In the few seconds following the core collapse, the energy radiated away as neutrinos exceeds the total energy the Sun will radiate as light across its entire 10 billion year lifetime. Not in a day, not in a year. The entire lifetime of the Sun, all 10 billion years of it, in a handful of seconds. The energy leaves not as light, not as heat in any ordinary sense, but as ghostly particles that pass through the surrounding star almost as though it were not there. 10 kilometers of nuclear density matter, the most compressed substance in the universe, is to a neutrino no thicker than a pane of glass to ordinary light. The vast pulse moves outward at nearly the speed of light, and most of it passes through the star and escapes into space without a single interaction. Most of it, but not all. A small fraction of the neutrinos are absorbed in the outer layers of the collapsing star. Even a fraction of an enormous number is an enormous number. The energy deposited by those absorptions is enough to reverse the infall of the outer layers, to drive them outward with enough force to overcome the star's own gravity, to send them flying outward at tens of thousands of kilometers per second. The collapsing core has bounced. The innermost material has reached nuclear density, as dense as an atomic nucleus, denser than anything ordinarily encountered in the universe, and it has stiffened, become rigid, and reflected the infalling outer core back outward as a shock wave. The shock wave moves out through the burning shells above the core. It passes through the silicon burning layer, through the oxygen, through the neon, the carbon, the helium, the hydrogen. Everything in its path is driven outward. Elements synthesized over 10 million years of stellar burning are expelled into the surrounding space. The star tears open. For a few days, the expanding debris glows brighter than anything else in the galaxy, bright enough to be visible in daylight from a planet orbiting a distant star, bright enough to cast shadows on a clear night even at enormous distances. A star has died, and its death is the brightest thing anyone in its neighborhood will ever see. At the center of all that expanding brilliance, in the place where the iron core collapsed, something very small and very dense remains. The proto-neutron star forms within the first second of the collapse, a sphere of neutrons roughly 50 to 100 kilometers across, and still enormously hot, hotter than 100 billion degrees in its interior, cooling rapidly through the emission of neutrinos, contracting as it cools. Over the next 10 to 30 seconds, it sheds the last of its thermal neutrino flux and settles into itself, its radius shrinking from dozens of kilometers to approximately 10 or 12. What remains is a stable neutron star, the compressed remnant of a core that once held more than a solar mass of iron, now holding that same mass in a sphere the size of a city, held up not by electron degeneracy, but by something more extreme, the pressure of neutrons themselves resisting compression, the quantum stubbornness of an entire species of nuclear matter packed to the density of an atomic nucleus across a volume 10 kilometers wide. The star that surrounded it for millions of years is gone. The burning shells are expanding outward at thousands of kilometers per second. The nuclear furnaces are extinguished. The iron core that could not burn has become something more extreme than fire ever produced. In the dark beyond the dead star, the expanding shell of gas and dust continues moving outward. It catches the thin material of the space between stars, the diffuse clouds of hydrogen and helium that permeate the galaxy, and compresses it, piling it up into a shell that glows and shocks and emits light across wavelengths from radio waves to X-rays. This expanding remnant carries within it the chemical history of the star that made it. Oxygen, carbon, neon, magnesium, all the elements built up over 10 million years of fusion in the star's nested shells, are dispersed now into the interstellar medium. The remnant is diffuse and thinning, its leading edge slowing as it sweeps up more mass, its glow fading over thousands of years as the energy in the shock dissipates into the surrounding space. In the year 1054, Chinese astronomers looked up from the northern Song dynasty and recorded a new light in the sky. It appeared in the constellation now called Taurus. It was bright enough to see during daylight. It held its position against the background stars, which ruled out a comet, and it did not move, which ruled out a planet. It faded slowly over the following weeks and months. After about 2 years, it was gone from unaided human sight. The astronomers noted it in their records, described it as a guest star, and the sky returned to the ordinary arrangement it had maintained through all the years of observation before that morning. What they had seen was the light of a stellar explosion reaching the Earth after traveling for 6,500 years. The star had already died before the last wild mammoths walked the Earth. The light of its death had been crossing space since before the construction of Stonehenge, since before the earliest cities of Mesopotamia, arriving at the Earth in the late spring of 1054 and entering the eyes of anyone who happened to look at Taurus before dawn. It arrived only once, and then it was gone, and the astronomers who saw it could not have known what had made it, or that their record of its appearance would one day become one of the most important astronomical observations in all of human history. What remained after the light faded, what remained in that patch of sky, whether anyone was looking or not, was a cloud of expanding gas and dust, and at its center, a tiny, dense, spinning object pouring energy into the cloud around it, keeping it glowing across the centuries. What that object is and how it works would not be understood for more than 900 years. The nebula that grew from the 1054 explosion is visible today through even a modest telescope. It spans roughly 11 light years across, a distance so large that light, moving at nearly 300,000 kilometers every second, would need 11 years to cross from one side to the other. It is still expanding, still moving outward from the point of the original explosion at roughly 1,500 kilometers per second, slower now than it was 970 years ago, slowed by the interstellar material it has been sweeping up across the centuries. Its surface is threaded with filaments of glowing gas, the expelled outer layers of the star, still radiating the energy they received from the explosion and from the dense object at the nebula's center. The colors vary by element and temperature. Hydrogen glows in red and pink. Doubly ionized oxygen shines in blue and green. The whole structure is luminous and irregular, ragged at the edges, a tattered shell of what was once a star's atmosphere expanding outward through the dark. At the center of the Crab Nebula, visible only through instruments sensitive to its rapid pulse, is the neutron star left behind by the collapse. It rotates 30 times each second. With each rotation, a beam of electromagnetic radiation sweeps outward from its magnetic poles and strikes the interior of the nebula, driving a wind of energetic particles that keeps the surrounding cloud illuminated. Without this central engine, the filaments would dim. The synchrotron glow of the high-energy electrons threading through the nebula would fade. The Crab Nebula, as it appears now, is not a passive remnant slowly dimming. It is actively powered, fed energy by the spinning neutron star at its center, which loses a small fraction of its rotational energy with each rotation and will continue doing so for thousands of years. Yet, the neutron star does not know this. It has no knowledge of the cloud it illuminates, no awareness of the filaments it powers, no memory of the star it once was, the core of. It spins because angular momentum is conserved, because the slow rotation of the large stellar core, compressed to a sphere 10 kilometers wide, becomes a rapid rotation that cannot simply dissipate. It emits because its magnetic field, stronger than anything on Earth by factors of trillions, accelerates charged particles along its poles into beams. It persists because the physics of compressed neutrons does not permit anything simpler. There is no will in any of this, no purpose, no goal. There is only the consequence of physical law operating at the most extreme conditions matter can reach. The 11 light-year cloud drifts outward through the Milky Way. The light that left it 6,500 years ago and reached the Earth in 1054 has now traveled to a distance 6,500 times farther. It has passed the edges of the galaxy's disk and is moving into the intergalactic medium, carrying in its photons the record of a death that happened before human writing existed. The astronomers who noted the guest star in their records are long gone. Their dynasty is long gone. Their records survive, copied and recopied across 1,000 years, and in those records the brightness and the date and the position preserved with the care of people who understood that what was unexpected was worth writing down. The cloud that their guest star left is still glowing. It will be glowing long after every person alive today is gone, long after the civilization that built the telescopes that now image it has ended and been replaced by whatever comes next. The expansion that began in the core collapse will continue for tens of thousands of years before the nebula finally becomes too thin and too cool to radiate. And through all of that time, in the faint central region of the expanding shell, the neutron star will be spinning a little slower each decade, a little dimmer each century, losing a fraction of its rotational energy as heat and light and particle wind, but still spinning, still dense, still an object of matter compressed beyond anything else in the known universe except the black holes, whose formation requires even more extreme conditions. There is something in the slow expansion of that cloud, in the way it moves outward through the galaxy at a pace too gradual to perceive in a human lifetime, in the way the gas and dust and the heavy elements it carries will one day slow enough to cool and condense and perhaps seed the formation of new stars, new planets, new chemistry that belongs to the deepest rhythm of things. Stars form, they burn. The burning produces the elements. The burning ends, and the ending produces other things: compression, shock, dispersal. The matter is not lost. The elements forged in the nested shells of a dying star do not vanish when the star explodes. They move outward into the space between stars and mix with the older material there, enriching it, making it heavier, making the next generation of stars a little more chemically complex than the last. The iron that could not burn became the seed of something other than fire. The outer layers of the star that died in 1054 are out there now, still moving, thinning, fading, stretched across 11 light years of space, and growing. In the slow middle of all that expansion, a small dense thing spins in the dark 30 times each second, unhurried and unchanged by the centuries since the light of its birth reached a set of human eyes who recorded it faithfully and then returned to their ordinary lives in a dynasty and a year and a world that have long since become history, under a sky that looked just the same by the following morning as it had every morning before. The nebula drifts. The light continues outward. The object at the center spins 10 kilometers. That is the number to hold at the start. Not a distance to travel, not a length of coastline or the span of a city park, but the full diameter of a star, a thing that was, not long ago in cosmic time, burning at the center of its own solar system, fusing hydrogen in its core, shining across billions of miles of empty space. 10 kilometers across, a little over 6 miles. The drive from one side of a modest American city to the other, past the hardware store and the quiet residential streets and the water tower on the hill at the edge of town. A neutron star fits inside that drive. The number sits still for a moment. It does not perform its own size. It simply rests there, asking to be held alongside the other number, the mass of the sun, which is itself 2 billion tons of hydrogen and helium, and trace heavier elements, a fire that has burned for 4.5 billion years and will burn for 5 billion more. A neutron star holds more than that. It holds the crushed remnant of a star far larger than our sun, and it holds it in a sphere 10 kilometers wide, and it holds it so tightly that the space between atoms, between nuclei, between the empty regions that make up almost all the volume of ordinary matter, has been pressed entirely away. There is no empty space inside a neutron star. There is nowhere left for emptiness to go. The surface of that sphere sits in silence. Not the silence of an empty room, but the silence of a place so remote from ordinary experience that no comparison to sound quite applies. In the space around a neutron star, there is no air to carry vibration, no medium to move, no way for any disturbance in the star's surface to reach an ear. What there is instead is gravity, a field so strong that the star's presence reshapes the geometry of space itself in its immediate vicinity. bending every path that anything might travel, including the path of light, which near the surface follows not a straight line, but a curve pulled measurably toward the star. Stand at a distance, a safe theoretical distance, millions of kilometers away, and measure the surface gravity of a typical neutron star. The number comes back at roughly 10 to the 12 meters per second squared. That means nothing by itself, so here is what it means in the world. On Earth, a person standing on the ground feels roughly 10 meters per second squared, pulling them down. On a neutron star, that same pull would be 200 billion times stronger. A small stone, released from 1 meter above the surface, would reach the surface in a fraction of a millisecond. When it struck, it would be traveling at close to half the speed of light. The impact would produce not a thud, but a nuclear-scale explosion, releasing more energy than any chemical reaction, enough energy to be visible across enormous distances, just from a pebble falling 1 meter. The number is not dramatic. It is simply the field generated by that much mass in that small a volume, and the field does not know to be impressed with itself. It sits there, curving space, pulling everything that comes near toward the surface, and it has been doing so for as long as the neutron star has existed. Across the range of neutron stars that astronomers have measured, masses cluster between roughly 1 and 1/10 to 2 and 1/3 times the mass of the Sun. The spread sounds small. In terms of what that mass does at a radius of 10 to 13 kilometers, it is enormous. The difference between a star sitting comfortably above its own gravitational limit and one perched so close to the edge that the distance between it and a black hole can be measured in a factor of 2 or 3. The most massive neutron star measured with confidence, a pulsar designated PSR J09520607, carries approximately 2 1/3 solar masses. That object is not much larger across than a medium-sized city, and it weighs more than 2 suns. The instrument used to measure it with precision is a telescope mounted on the International Space Station, watching X-rays from the star's hot surface as it rotates, reading in the timing and spectrum of that radiation the fingerprints of mass and radius that nothing else could provide so clearly. Inside a neutron star, the density exceeds anything achievable in a terrestrial laboratory by many orders of magnitude. In the deep core, matter may reach densities 10 to 100 times greater than the density of an atomic nucleus, which is itself the densest ordinary state. Matter is known to occupy. An atomic nucleus is already almost inconceivably dense. The protons and neutrons packed inside it are pressed against each other with no room to spare, held in place by the strong nuclear force, and their combined density is roughly 200 trillion kilograms per cubic meter. A neutron star's interior reaches that density and then surpasses it, pressing into a regime where the equations physicists use to describe nuclear matter begin to strain, where terms must be added to account for effects that have never been measured in any laboratory, where the physics becomes genuinely new territory. The core of a neutron star is the only place in the universe, as far as anyone knows, where matter reaches such densities outside a black hole's event horizon, and a black hole reveals nothing about what happens there, while a neutron star, at least, can be measured from the outside. Here is one way to feel the density. A single teaspoon of material drawn from the interior of a neutron star would weigh approximately 10 million metric tons. Not 10 million pounds, 10 million metric tons. That is more than the combined mass of every ship at sea, every aircraft in the air, every truck on every highway, every car in every parking lot on Earth, gathered into a volume the size of a sugar cube, and resting in this thought experiment on a kitchen table. The table would not survive. The floor beneath it would not survive. The teaspoon would fall through the earth as if the earth were not there, pulled by its own gravity toward the center, not stopping until it reached something dense enough to support it, which on earth nothing is. The number is not meant to alarm, it is meant to sit, quietly, as a measure of how far outside the range of ordinary matter a neutron star exists. The kitchen table in this image is not being threatened. It is simply the familiar object closest to hand, offered as a scale reference for something that lives in an entirely different part of the universe's catalog of densities. The surface of a neutron star, in the centuries immediately after the star forms, glows, not in visible light, or not primarily. The surface temperature of a young neutron star reaches into the tens of millions of Kelvin, far hotter than the surface of the sun, far hotter than any fire or plasma that can be generated on Earth. At those temperatures, the thermal radiation peaks in the X-ray band, far above the energies that correspond to visible light. The star is radiating brilliantly, flooding its immediate surroundings with high-energy photons, but a human eye placed at a safe distance would see very little. The energy is in the wrong part of the spectrum. It is X-ray light, invisible to biology, detectable only with instruments sensitive to short wavelength radiation. Across thousands and then millions of years, the surface cools. The star has no fuel, no fusion, no chemical reaction, no source of ongoing energy other than the gravitational compression that formed it and the slow leak of heat from its hot interior. It cools primarily by radiating neutrinos from deep inside, an emission that carries away enormous quantities of energy in the first 100,000 years or so. After that, as the interior drops below the threshold where neutrino production is efficient, the cooling slows, and the surface photon emission takes over as the dominant loss mechanism. The star continues to fade, its X-ray glow, dimming decade by decade, century by century. By the time 1,000,000 years have passed, the surface temperature has dropped to around 1,000,000 Kelvin. That is still enormously hot by any terrestrial standard, hotter than the corona of the sun, but it represents a cooling of more than 100-fold from the star's earliest days. The X-ray emission that was once brilliant has become a faint whisper, detectable only by sensitive space-based observatories looking carefully in the right direction. Eventually, in tens of millions of years, the surface temperature drops below the threshold, where even X-ray observatories can pick up the signal. The star becomes dark, not in the sense of a room with the lights off, but in the sense of matter that has given away nearly all the heat it was given at birth and now drifts through interstellar space at a temperature closer to the cosmic background, cold, dense, city-sized, invisible. If such a star passed close to Earth, astronomers would not know it from its light. They would know it only from what it did to the light of other things nearby, the gravitational lensing signature of a massive, compact object moving through the field of background stars, bending their images in ways that tell of density and mass without telling of brightness. There are almost certainly many of these dark, cold neutron stars drifting through the galaxy. The Milky Way is estimated to contain more than 1 billion neutron stars, the accumulated remnants of all the massive stars that have lived and died over the galaxy's 13 billion year history. Only a small fraction of those have been observed directly through their radio pulsar emission or their X-ray glow. The rest are silent, scattered through the arms of the galaxy, slowly cooling toward the temperature of the space around them, carrying their extraordinary mass and density through enormous stretches of empty space without announcement. One of the ways a neutron star makes itself known while it is still young enough to be seen is through the behavior of its light. A photon leaving the surface of a neutron star does not simply travel outward at a steady speed and arrive at a distant telescope unchanged. It climbs away from the star's enormous gravitational field, and in doing so it loses energy to that field, a process called gravitational redshift. The photon arrives at the telescope slightly less energetic than when it left the surface. Its wavelength has stretched. If it left the surface as an X-ray photon, it arrives shifted toward lower energies, and the amount of the shift depends precisely on how strong the gravitational field is at the point of departure, which depends on the ratio of the star's mass to its radius. This is not a correction or a technicality. For a neutron star, the gravitational redshift is large enough that it can be measured from thousands of light years away, and it encodes directly in the spectrum of the star's light, a number that constrains both the mass and the radius simultaneously. The photon carries in its wavelength a record of the gravity it climbed through. It arrives at the telescope stretched, visibly, measurably, and the stretch read against what the photon's wavelength should have been tells the observer how compact the star is. A star of greater compactness produces a greater redshift. A star closer to the boundary of its own gravitational limit shifts its photons more than one, sitting farther from that edge. The escape velocity from the surface of a typical neutron star lies between 100,000 and 150,000 kilometers per second. At the lower end of that range, that is 1/3 the speed of light. At the upper end, it approaches 1/2. This means that any photon leaving the surface, any light at all, begins its journey fighting against a gravitational field so intense that a significant fraction of the photon's energy is consumed just in escaping. It is also what would be required of any particle, any piece of matter, any object of any mass, to leave the star's surface without falling back. A rocket attempting to leave the surface of a neutron star would need to reach 1/3 of the speed of light before it had gone anywhere at all. Nothing achievable by any propulsion technology remotely conceivable would produce that speed, and so the surface of a neutron star is in any practical sense unreachable from the outside and unescapable from below. These are not thought experiments designed to illustrate difficulty. They are the direct consequences of general relativity applied honestly to an object of that mass and radius, and general relativity does not stop being the dominant framework here, as it does for ordinary stars or planets. For an ordinary star, general relativity is a small correction to Newtonian gravity, a refinement that matters only for very precise measurements. For a neutron star, it is the whole story. The bending of light near the surface, the gravitational redshift, the way time itself runs slightly slower close to the star's surface than far from it. These are not peripheral effects. They are the central physical description of everything happening in the star's immediate vicinity. Time runs slower near the surface of a neutron star, not by a small amount, by a factor that is measurable and significant. A clock placed on the surface of a neutron star would tick more slowly than an identical clock far away, and the difference would be large enough to matter. A second at the surface would correspond to several seconds far from the star. The star does not know this, and the clock does not know this, and the difference is not an illusion or a measurement artifact. It is the actual physical rate at which time progresses, altered by the depth of the gravitational well. The same effect exists on Earth and near the Sun, and it has to be corrected for in GPS satellites, whose clocks run at slightly different rates than clocks on the ground. Near a neutron star, the effect is not a correction. It is the dominant feature of how time flows. The Schwarzschild radius of a neutron star, the radius at which, if all the star's mass were compressed inside it, the star would become a black hole, sits only a factor of 2 or 3 below the star's actual radius. The star and its own gravitational boundary are not far apart. An ordinary star like the Sun has a Schwarzschild radius of roughly 3 kilometers. The Sun's actual radius is close to 700,000 kilometers. The Sun would have to shrink by a factor of 200,000 to cross that boundary. A neutron star with a radius of 12 kilometers has a Schwarzschild radius of perhaps 5 or 6 kilometers, depending on mass. It exists, at every moment of its existence, in the condition of permanent proximity to its own gravitational threshold, separated from it not by vast distances, but by a few kilometers of stable nuclear matter and the pressure that holds it. This is a different kind of existence from anything else in the observable universe. A white dwarf star, also a stellar remnant, is larger and less dense, supported by the pressure of electrons rather than neutrons, and it sits comfortably far from its Schwarzschild radius. A planet, a moon, a cloud of gas, and a nebula, all of these objects are so far from their own gravitational limit that the concept does not meaningfully apply to them. Only a neutron star and a black hole which has already passed the limit occupies this particular place in the diagram of physical possibility. The neutron star is as close to a black hole as a stable object can be. There is a quality to this that is on reflection deeply restful to consider, not the violence of the formation which belongs to the star's past, not the energetics of a pulsar which belongs to other stars in other conditions, but the settled, stable state of a cold or cooling neutron star, drifting in the dark, carrying its enormous density and its proximity to the gravitational edge with complete equanimity, neither approaching nor retreating, simply existing in a condition that has no close analog anywhere else in the physical world. The surface gravity that would destroy any ordinary object is merely the surface gravity. The compactness that means space itself is measurably curved at the star's surface is merely the compactness. The star does not press against its limits. It inhabits them, the way a stone at the bottom of a river inhabits the pressure of the water above it, not straining, not struggling, simply resting in the condition of its own existence. In the center, the density is highest, not the density of the surface layers, already extraordinary by any terrestrial measure, but a density that increases inward through the star's interior as the weight of the outer layers compresses the inner ones. The exact conditions at the center of a neutron star are not fully understood, and there is no pretense otherwise. The equations of nuclear physics can describe matter up to roughly the density of an atomic nucleus with reasonable confidence, but at 2 or 3 times that density, the conditions expected in the deepest core. The equations begin to offer several possibilities rather than one clear answer. The behavior of matter at those extremes has never been measured in any experiment. It cannot be reproduced on Earth. What lives at the center of the densest stars is a question that current physics answers, not with certainty, but with a range of models, each consistent with what can be observed from the outside, none yet confirmed as correct. The outer edge of the star is more accessible, in the sense of being better described by known physics, though it too is far from ordinary. The surface is not a gas or a liquid, but something closer to an extremely dense crystal, atomic nuclei locked in a rigid lattice under conditions no mineral has ever experienced. Electrons moving freely through the lattice like a sea, rather than bound to individual atoms. Below that surface, the density climbs. The nuclei in the lattice grow heavier and more neutron-rich, and at a certain depth, the nuclei can no longer hold all the neutrons they contain. The neutrons begin to drip out, moving freely through the material, and the character of the matter changes again. Deeper still, the lattice dissolves entirely, and what remains is a dense fluid of neutrons and other particles, carrying the weight of the entire outer star on its invisible shoulders, supporting it through quantum mechanical pressure rather than through any force a macroscopic object would recognize. At the very center, something, and the something is genuinely uncertain, supports the innermost layers. Whether that something is neutrons alone, or the strange heavier particles that emerge at high density, or the fundamental quarks that make up those particles moving freely in a kind of plasma, or some combination of phases arranged in layers like geological strata, is not known. The star holds its center private, and the only way to read it is through the behavior of the whole star observed from outside, its mass, its radius, the way it vibrates after certain disturbances, the way it changes over time. Those observations are ongoing. The answers, when they arrive, will come from telescopes and gravitational wave detectors, reading the star's exterior with increasing precision, slowly inferring what must be inside. A neutron star approximately 12 kilometers across, holding 1.5 times the mass of the Sun, drifts through the space between stars. Its surface, if this star is old enough, has cooled to a temperature that produces no visible glow. The space around it is not empty. Interstellar space is threaded with gas and dust at very low density, but nothing in the surrounding medium is compressed or disturbed by the star's passage. The star moves through the galaxy at perhaps a few hundred kilometers per second relative to the background stars, a speed that is fast by human standards and routine by stellar ones. It carries with it the record of a supernova explosion that happened millions of years ago, the compressed remnant of a star many times more massive than it is now, the accumulated debris of nuclear burning across millions of years of stellar life pressed into a sphere too small to see from a distance with the naked eye. Nothing in the galaxy knows it is there, except indirectly through the gentle gravitational influence it exerts on everything in its vicinity. Stars at a considerable distance feel the faint tug of its mass as it passes, bending their trajectories by amounts too small to notice over any human lifetime. The star does not announce itself. From a distance of several light years, the distance to the nearest stars from our own sun, this neutron star is invisible. No telescope pointed at the empty patch of sky where it drifts would see it. No optical observation would reveal it. Only the subtlest gravitational lensing signature, or the chance that it one day accretes enough material from a passing gas cloud to flare back into X-ray visibility, or the possibility that a future generation of detectors will be sensitive enough to map the mass distribution of the galaxy from the gravitational influence of all its hidden objects combined, would give it away. It drifts, it cools, the space around it is unlit. Somewhere nearer to the center of the galaxy, where stellar density is higher and the rate of stellar death has been correspondingly greater, many such objects drift together, not close enough to interact, separated by light years, but sharing the same general region of space as the accumulated remnants of a galaxy's long violent history. 1 billion or more neutron stars in the galaxy, most of them invisible, most of them cooling toward the temperature of the surrounding medium across timescales that make a human civilization look like a momentary flash. And somewhere in that vast dark inventory, a young one, a few thousand years old, still radiating in X-rays, its surface at temperatures of a few million Kelvin, glows faintly against the blackness, its spectrum containing in every photon it emits the gravitational fingerprint of its mass and radius, waiting for an instrument sensitive enough and pointed in the right direction to read it. The photons leave the surface. They climb. As they climb, the gravitational field of the star pulls at them, stretching their wavelengths, draining a fraction of their energy into the curved space they are passing through. By the time they reach open interstellar space, they are slightly redder, slightly less energetic than when they left. They continue outward at the speed of light, carrying their redshift with them, traveling through the dark for however many thousands of light years separate the star from whatever telescope is waiting. They have been traveling since before any human set eyes on the sky. The telescope receives them. It records their wavelengths. Someone, somewhere, reads the spectrum and measures the shift. The mass and radius of the neutron star, the parameters that govern everything about the star's structure, that constrain what the core is made of, that determine how close the star sits to its own gravitational boundary, are present in that measurement, encoded in wavelengths of X-ray light, stretched by the climb through a gravitational field 12 kilometers deep. The measurement is complete. The star continues to drift, unaware, in the dark. The photons that carried its information continue past the telescope, spreading outward through the universe at light speed, carrying their stretched wavelengths farther and farther from the star that made them, until eventually, over timescales that have no correspondence to anything human, they thin past detectability, and the record they carry is lost in the background radiation of the cooling universe. But for the moment of the measurement, the star was known. Its mass and radius sat on a graph alongside other measured neutron stars, constraining the equations that describe dense nuclear matter, narrowing the range of what is possible at densities that no laboratory has ever achieved, contributing one more point of contact between the theoretical and the observed. The star did not know it was being measured. It continued to drift. The cooling continued, patient and unhurried, as it has continued since the star formed, and as it will continue for tens of millions of years more, until the surface drops below the last threshold at which any instrument could detect it, and the star becomes, in every practical sense, invisible to everything, cold, dense, alone in the dark between stars, 12 kilometers wide and heavier than the sun, pressing the boundary of its own possible existence in permanent, effortless stillness, the way deep water presses the floor of a trench, not urgently, not dramatically, but with the full weight of everything it is, quietly, without end. The surface of the star holds no feature that any human sense could register at a distance. There is no fire on the surface of a cold neutron star, no flame, no glow perceptible to an eye. What there is in the crystalline structure of the outer layers is order, a geometric regularity imposed by the conditions of formation, nuclei arranged in a lattice under pressures that would be lethal to any ordinary matter, held in place by forces too small to feel at any scale larger than the subatomic. Somewhere deep in that lattice, at depths measured in hundreds of meters below the surface, the geometry begins to blur. The regular crystal gives way to something stranger, matter adopting shapes that have no analog in any terrestrial mineral, forms determined by the balance between nuclear attraction and electromagnetic repulsion at densities that do not exist anywhere on Earth. And below that, deeper still, a fluid of free neutrons moves in slow currents, carrying no light, producing no sound, supporting the weight of the crust above, and pressing upward against it with the gentle, implacable pressure of quantum mechanics applied to matter, far beyond ordinary nuclear densities. The star holds all of this inside 10 kilometers. the emptiness outside is much larger. In every direction from the star's surface, for light years in each direction, there is almost nothing, gas too thin to see, dust too sparse to matter, the occasional photon crossing from a distant source. The star occupies a region of space many orders of magnitude smaller than the void that surrounds it, and the void does not know the star is there, and the star does not know the void. They coexist without drama, the dense and the empty, the 10-kilometer object and the light years of nothing, the weight of more than a sun, and the near perfect vacuum of interstellar space. In this, the star is like every other object in the universe, surrounded by an immensity of distance that makes its own extent almost negligible. A galaxy is mostly empty, a star system is mostly empty. The space between stars is almost entirely empty, and the neutron star is a small, cold, dense exception to all of that emptiness, a place where matter condensed to the point where empty space itself was expelled, carrying its extraordinary properties through a universe that barely notices its passage. The numbers that describe it, the 10 kilometers, the 1.5 solar masses, the density of 100 million tons per teaspoon, the surface gravity 200 billion times Earth's, the escape velocity a third of the speed of light, do not diminish with repetition. They sit the same way each time, heavy and quiet and precise, describing an object that exists without apology at one of the outer edges of the physical world, stable, unhurried, and enduring, while around it the universe continues to expand and cool and thin, as it has been doing for 13 billion years, and as it will continue to do for far longer. The neutron star drifts on, carrying its ancient interior and its measured exterior and its slow thermal decline through the dark, one more dense and patient remnant in a galaxy full of them, cooling as the rest of the universe also cools toward the deep, eventual stillness that waits at the end of all things, long and unhurried, and for now impossibly far away. Below, the crust begins, not with a sharp edge or a visible line, but with a gradual change in the character of matter, a deepening, a compression, a shift in what atoms are capable of holding together. The surface of the neutron star lies just above, a place of strange, smooth topography, no more than a few centimeters high in its tallest features, bathed in the violet overflow of X-ray light. And beneath it, descending through layers no instrument has ever reached, and no human mind has ever directly pictured, something extraordinary is happening in the dark. The outer crust starts like a mineral, not a mineral anything on Earth resembles, but something with the same essential quality, a repeating geometric arrangement of atomic nuclei, locked in place by electromagnetic force, spaced at regular intervals, each one sitting in a fixed position in a lattice that extends outward in all directions. The nuclei near the very surface are made of iron, 56 protons and neutrons bound together, the same iron that sits at the end of every fusion chain a massive star can run. They are small and regular and densely packed, sitting in a sea of free electrons that moves between them like a current through a conductor, and under pressures that no laboratory on this planet has ever reproduced. The gravity pulling down on every layer of this crust is 200 billion times the pull felt at the surface of the Earth. Every gram of matter above presses down on the gram below with a weight that has no familiar counterpart. Yet the lattice holds, the crystal structure of the outer crust persists, because the electromagnetic repulsion between nuclei balances the pressure from above, and the electrons threading through the spaces carry the load the way a fluid carries pressure, evenly, in all directions, without yield. Going deeper, the pressure climbs. It climbs not in the way pressure climbs in the ocean, where every foot of water adds a small calculable weight. It climbs in a way that changes the fundamental character of matter itself. As the density rises through the outer layers of the crust, the nuclei respond by absorbing more and more neutrons. They grow heavier. The proportion of neutrons within each nucleus increases until the nuclei sit far off the island of stability that governs ordinary matter. Grotesque, neutron bloated structures that no earthly chemistry could produce or sustain, but that here, under this particular pressure and density, bear the natural equilibrium. Roughly a third of a mile below the surface, something changes in the fabric of the crust. The nuclei have grown so heavy with neutrons that they can no longer hold all of them. Neutrons begin to drip out. Not violently, not in a burst, but as a slow leakage, individual neutrons released from the edges of nuclei and entering the surrounding space as free particles moving through the lattice in a thin, cold quantum fluid. This is called the neutron drip point, and it marks the boundary where the inner crust begins and where the physics of the interior becomes something entirely its own. The free neutrons fill the inner crust like a slow river, filling every gap in a stone wall. They are not a gas in the ordinary sense. They are governed by quantum mechanics in a way that gas molecules are not, by the exclusion principle that prevents identical fermions from occupying the same state, by the wave nature that makes their positions inherently spread across the spaces between nuclei. They thread through the crystalline lattice of heavier and heavier nuclei, adding their own pressure to the sum of forces holding the star's layers apart, and the nuclei themselves continue to change. As the density rises through the inner crust, the heavy nuclei that anchor the lattice grow so large and so irregular that their geometry begins to blur. The boundary between a very large nucleus and the surrounding free neutron fluid becomes less distinct. The nuclear matter starts exploring shapes that ordinary nuclei never adopt, not the familiar sphere of a nucleus in free space, but extended forms driven by the competition between the nuclear strong force, which pulls nuclear matter together at short range, and the electromagnetic force, which pushes protons apart at all ranges. In a thin layer close to the base of the crust, a few hundred meters down, matter may arrange itself into structures that nuclear physicists have given informal names, borrowed from the kitchen, because the shapes they describe, calculated on paper, never seen, are genuinely reminiscent of food. Long cylinders of dense nuclear matter embedded in a sea of less dense matter, like rods. Flat sheets of nuclear matter interleaved with gaps, like layers. Spherical holes in otherwise continuous nuclear matter, like voids in a sponge. The shapes shift as density increases, each one a different solution to the same competition between forces, and the whole sequence is called nuclear pasta, a name both improbable and accurate for some of the most extreme material structure that physics predicts anywhere in the universe. The nuclear pasta layer is believed to be among the strongest materials that can exist. Calculations suggest it would take a stress 10 billion times greater than the stress that breaks the strongest steel on Earth to fracture it. Whether this is exactly right, no one can be sure. There are no samples to test, no experiment that could reproduce the conditions, and the models that generate these numbers are built from nuclear theory, extrapolated far beyond anything measurable in a laboratory. The pasta layer carries its strength in quiet obscurity, a few hundred meters thick, somewhere inside an object too small to see from 100 light years away. Below the pasta layer, the crust ends. There is no hard boundary. The transition from crust to core is gradual, a smooth increase in density, rather than a sudden change in character. But somewhere near the base of the inner crust, the dense nuclear clusters dissolve entirely into a continuous fluid of nuclear matter. The lattice that defined the crust is gone. What remains is something that has no name in ordinary condensed matter physics and no analog on Earth. A dense continuous sea of neutrons with a small admixture of protons and electrons, all under pressures that no terrestrial experiment will ever reproduce. This is the outer core, and it begins roughly 1 kilometer below the surface and extends inward through the bulk of the star's volume. The density here is already comparable to the density inside an atomic nucleus. The density, in other words, at which protons and neutrons sit in the hearts of familiar atoms. In ordinary matter, nuclear densities exist only in the nucleus itself, a region a few femtometers across. Inside the neutron star's outer core, nuclear densities extend across a volume kilometers in diameter. The scale of the familiar and the scale of the extreme have traded places entirely. In this region, under these conditions, the neutrons are believed to do something that nothing at human scales does. They pair up. Not in the way electrons pair in a superconductor, though the analogy is close enough to be instructive. Neutrons in the dense fluid of the outer core are predicted to form loose pairs bound together by the residual effects of the strong nuclear force. Cooper pairs, after the physicist whose name the phenomenon carries in the context of electrons, though the underlying mechanism is similar. And when particles form pairs in this way, and the temperature is low enough, those pairs condense into a quantum state in which vast numbers of them share the same collective behavior. The fluid loses all viscosity, it flows without resistance, it rotates without friction. It is, in the language of quantum mechanics, a superfluid. A neutron superfluid is one of the strangest states of matter that physics predicts. It cannot be poured or held or examined in any direct sense. Its existence inside neutron stars is inferred from behavior observed at a distance, from small, precise anomalies in the timing of the pulses that some of these stars emit. But the strangeness of its properties is not diminished by the indirectness of the evidence. A superfluid cannot rotate the way ordinary matter rotates. In ordinary matter, every small element of the fluid rotates with the fluid as a whole. The angular velocity is smoothly distributed across the material. A superfluid cannot do this. Instead, it rotates by developing quantized vortices, thin, thread-like structures, each one carrying a fixed, indivisible quantum of rotation, arranged in a lattice that threads through the rotating fluid, the way poles in a field fence, a pasture. The more rapidly the fluid rotates, the more vortices it contains, and the vortex lattice carries the rotation in discrete units rather than as a smooth gradient. Inside the outer core of a neutron star, this lattice of quantized vortex lines fills the superfluid volume, billions upon billions of them, each one a thin tube of rotating matter, arranged with a regularity that mirrors the lattice of the crystal crust above. They spin silently in the dark interior, invisible, carrying the entire rotation of the superfluid in a structure no sensor can reach, and the crust above them matters. The vortices in the neutron superfluid interact with the crystalline crust that borders them. They can pin to the lattice sites of the crust, attach in a quantum mechanical sense to particular positions in the nuclear crystal, and when they are pinned, they resist being moved. As the neutron star slows down over time, losing rotational energy to the radiation it emits, the superfluid vortices need to move outward, carrying away angular momentum, allowing the fluid to spin more slowly. But if the vortices are pinned, they cannot move smoothly. Instead, they accumulate stress like a spring being wound, and then periodically they release a sudden unpinning of a large number of vortices at once, a brief and violent transfer of angular momentum from the superfluid to the crust, and from the crust to the rest of the star. From outside the star, this appears as a glitch. The star has been spinning steadily, its pulses arriving with the regularity of a clock, the interval between them growing almost imperceptibly longer as the star slows. Then, briefly, the pulses arrive fractionally too early. The rotation has increased, not by much, but measurably by a part in a million or less, depending on the star, and then it declines again, sometimes over days, sometimes over months, returning toward the trend. The glitch lasts no longer than a heartbeat in the life of the star, but in the data of the astronomers watching, it is a window into a process occurring kilometers beneath the surface. The Vela pulsar, a neutron star in the southern sky, roughly 1,000 light years away, is the most watched source of these events. It glitches more frequently than almost any other known pulsar, several times per decade in some analyses, and the pattern of its glitches has occupied theorists for more than 50 years. The sizes, the frequencies, the recovery profiles all contain information about the fraction of the star's moment of inertia that participates in the sudden transfer, about the pinning strength of the vortices, about the superfluid's coupling to the solid crust. No one has yet extracted a single clean, agreed picture from all of this data. The glitch mechanism is real and well observed, and the broad outlines of the superfluid explanation are widely accepted, and the fine details remain genuinely open. The star does not announce what is happening inside it. It continues to rotate, continues to slow, continues to emit its steady pulses across the dark, between it and the instruments watching it, and in the occasional small deviation from perfect regularity, it leaves a trace of what lives in its interior. Deeper still, the picture grows less certain. At densities roughly 2 to 3 times the density at the center of an ordinary atomic nucleus, the physics of the neutron star's core enters territory where nuclear theory has real footing and real uncertainty at the same time. The equations that govern nuclear matter are well tested at nuclear saturation density, the density at which protons and neutrons sit in familiar atomic nuclei. But as density increases beyond that point, those equations must be extrapolated, and extrapolation always brings error, and in some directions it may bring qualitatively wrong predictions. What happens to matter at 3 times nuclear density is not known from experiment. It is known only from models, and the models disagree with one another in important ways. One of the central disagreements concerns a family of particles called hyperons. In ordinary matter, the matter of everyday objects, of the human body, of the Earth, the only stable baryons are the proton and the neutron. These are the lightest members of the baryon family, the particles made of 3 quarks bound together by the strong force. Heavier baryons exist, particles built from quarks that include the strange quark, heavier than the up and down quarks that compose protons and neutrons. But these heavier baryons are unstable in free space. They decay in tiny fractions of a second into lighter particles and are gone. Inside a neutron star's deep core, the situation may change. At sufficiently high densities, it can become energetically favorable for a neutron to transform into a heavier baryon, containing a strange quark, a hyperon, rather than remaining a neutron. The neutron's rest energy is high enough that at extreme densities, converting it into a hyperon and a lighter particle might actually lower the total energy of the system. The hyperons could then accumulate in the core, forming a significant fraction of the deep interior's composition. This sounds plausible, but it runs into a serious problem. Hyperons, if they appear, soften the equation of state. The equation of state is the relationship between pressure and density in the stellar material, essentially a description of how stiff or compressible the matter is. A softer equation of state means lower pressure at a given density, and lower pressure means less support against gravity, and less support against gravity means a lower maximum possible mass for the star. The models that include hyperons typically predict maximum masses well below 2 solar masses, but neutron stars with masses close to 2 solar masses have been measured. Two of them, PSRJ 1614, 2230, and PSRJ 09520607, have been found with masses in that range through precise pulsar timing, and their existence rules out any equation of state that cannot support them. If hyperons appear and soften the matter as the models suggest, those stars could not exist. Yet they do exist. This conflict between the theoretical prediction that hyperons should appear and the observational fact that stars remain massive enough to rule out the softening those hyperons would cause is called the hyperon puzzle, and it has not been resolved. Perhaps hyperons appear but interact strongly enough with one another to restabilize the matter at high density. Perhaps the strong force behaves differently in bulk nuclear matter than in free space, and the repulsive components of the nuclear force stiffen the equation of state enough to compensate. Perhaps the models that predict hyperon appearance are missing important physics. Or perhaps hyperons do not appear in neutron star cores at all, and the question is moot. No one knows yet. The puzzle sits in the equations, patient and unresolved, and the observations that could settle it are not yet precise enough to do so. Deeper still, at the very center of the most massive neutron stars, the density may reach a threshold where the concept of a neutron itself begins to dissolve. A neutron is not a fundamental particle. It is a composite object, 3 quarks, 2 of one type and 1 of another, bound so tightly by the strong force that in ordinary nuclear matter they have no independent existence. They are confined, in the language of quantum chromodynamics, the theory of the strong force, confined to the interior of the baryon. They constitute, unable to propagate freely, never found isolated in ordinary conditions. This confinement is one of the remarkable properties of the strong force. It grows stronger, not weaker, as quarks are pulled apart, so that separating them requires more and more energy, until it is cheaper to create a new quark-antiquark pair than to continue the separation. But confinement depends on density. In ordinary nuclear matter, the individual baryons are well separated. There is space between them, and the quarks inside each baryon have no opportunity to wander into adjacent baryons. As density increases, the baryons are pressed closer together. Their boundaries begin to overlap. The quarks inside adjacent baryons begin to find that the space available to them extends beyond the boundary of a single baryon. At some critical density, exactly what density is not known. The individual baryon identities may cease to be meaningful, and the quarks may become free to move through the entire volume of the dense matter, no longer confined to any single bound state. This would be a quark-gluon plasma, or something close to it, a state of matter in which quarks and the gluons that carry the strong force between them move freely rather than being bound into composite particles, and more. Something resembling this state is produced briefly in high-energy particle collider experiments, when heavy atomic nuclei collide at close to the speed of light and produce a tiny, short-lived fireball of deconfined quark matter. But the quark matter predicted at the centers of massive neutron stars would be cold by the standards of quark matter, cold and dense, not hot and sparse, and the physics of cold, dense quark matter is considerably harder to calculate than the hot variety. There is a further possibility, stranger still. In 1984, the physicists Edward Witten and Arnold Bodmer, working independently, proposed that the true ground state of matter, the lowest possible energy configuration that matter can adopt, might not be ordinary nuclear matter at all, but a form of matter in which equal numbers of up, down, and strange quarks are present, bound together without being confined into individual baryons. This is called strange quark matter, and if the Bodmer-Witten hypothesis is correct, it would be more stable than any ordinary nucleus. Every atomic nucleus in the universe would be in a metastable state, like a ball resting in a shallow valley, with a deeper valley just over the ridge. In practice, converting ordinary matter into strange quark matter would require the simultaneous rearrangement of an enormous number of quarks, an event so unlikely that the universe can persist in its metastable ordinary nuclear state, essentially forever. But in the heart of a neutron star, where densities are extreme and the matter is compressed until baryon identities begin to overlap, the conversion might become possible. If the core of a massive neutron star does transition to strange quark matter, the object would technically no longer be a neutron star at its center. It would be something else, a hybrid with ordinary hadronic matter in its outer layers and a core of strange quark matter at the center. Whether any of this happens is not yet known. There is no observation that unambiguously requires a quark core. There is no observation that unambiguously rules one out. The best current constraints on the equation of state come from a combination of methods, from the precise timing of pulsars and binary systems, from the X-ray observations of neutron star surface temperatures and sizes gathered by the NICER telescope aboard the International Space Station, and from the gravitational wave signatures of neutron star mergers. Each of these methods provides a different kind of pressure on the space of possible equations of state, eliminating models that predict properties inconsistent with measurements and narrowing the range of acceptable ones. Together, these constraints are beginning to suggest that a typical neutron star, one with a mass of about 1 4/10 times the mass of the Sun, has a radius somewhere between 11 and 13 kilometers. This is a range, not a single number, and it carries its own uncertainties, but it is considerably more precise than what was known even a decade ago. Each refinement in the radius estimate is, indirectly, a refinement in the equation of state, and a refinement in the equation of state is a step closer to understanding what matter is doing in the places no instrument has directly reached. The descent through the interior comes to rest at the center. A few kilometers in every direction from that deepest point, a distance roughly equivalent to the length of a city block, repeated a few thousand times, lies the boundary of the core, and at the center itself, the density reaches its highest value, the pressure bears its greatest weight, and the nature of the matter that occupies that small dark region remains at the current edge of knowledge, genuinely unknown. This is not a gap in physics that suggests physics has failed. It is a gap in physics at the edge of where physics has been tested. The equations of quantum chromodynamics are believed to be correct. They have been verified with extraordinary precision at the energies accessible to particle physics experiments, but applying them to cold, dense matter at several times nuclear saturation density requires techniques that have not yet been perfected. Lattice calculations, which are the most reliable first principles approach to strongly interacting matter, become computationally intractable at high baryon density. Perturbative approaches, which work at extremely high densities where the strong coupling weakens, cannot yet be connected smoothly to the moderate densities that actually occur in neutron star cores. The theoretical methods available are sophisticated and carefully developed and genuinely insufficient to resolve the question. And so the interior of the neutron star holds its secrets, not by concealing them, but simply by being a place that no light leaves, no particle escapes from, and no probe can ever reach directly. The information that filters outward through the surface, through the pulses, through the X rays, through the gravitational ripples that pass through space-time when two of these stars collide, is all there is. Physicists assemble the interior picture from the outside in, like reconstructing a sculpture from its shadow, a painstaking incremental work in which each new observation adds a constraint, and the full picture remains, for now assembled only in hypotheses and equations. The depth is permanent. The star will not open. The questions will not be answered by looking harder at the surface, or by waiting for the star to offer up something new without prompting. Every advance in the understanding of what lives inside these objects will come from more precise measurement at the boundary, from better X-ray telescopes measuring the surface more carefully, from longer baseline pulsar timing, picking out tinier deviations, from gravitational wave detectors, sensitive enough to distinguish the ring-down frequencies of post-merger remnants, and from theoretical work that closes the gap between what the fundamental equations say and what dense matter actually does. In the meantime, the star continues. It rotates. It cools very slowly by the vast timescales that govern the cooling of these objects. It carries its crust, its superfluid interior, its uncertain deep core, its pinned vortex lattice, and its layer of nuclear pasta through space at whatever velocity it has carried since it was born, and it makes no announcement about the nature of its interior, and it does not require an audience. It has been this way since the supernova that made it, tens of thousands of years ago, or 1 million years ago, or more. It will remain this way for billions of years ahead, cooling slowly toward the temperature of the space around it, its rotation unwinding over geological timescales, its deep core holding whatever it holds in silence. Somewhere in the crust, a vortex line unpins. The angular momentum transfers, fractionally, upward through the layers, from the superfluid to the crystal lattice to the surface of the star, and the rotation changes by a part that instruments on the other side of the galaxy can register as a small deviation in the timing of a pulse. Then the timing returns to its steady decline. The crystal settles. The superfluid resumes its slow, constrained motion through the lattice of vortices. Everything is as it was. The nuclear pasta sits below, denser than anything that can be broken or tested. A few 100 meters of the most resistant material structure in the known universe, holding the geometry of competing forces in its sheets and rods and voids. The free neutrons flow between the nuclei of the inner crust, a quantum fluid threading through a crystalline scaffold under pressures that no number meaningfully conveys, in a region that no probe will ever enter. And at the center, at the deepest point, the matter sits in whatever state it is in, under the weight of everything above it, in the dark that has been there since the first second after the core collapse, before the supernova had even reached the surface of the dying star. The density is what it is. The pressure is what it is. The quarks, if they have come free, move through the small dark volume without confinement, or they remain bound inside baryons, or they form something in between that the equations have not yet correctly described. The star does not know, in any sense of knowing, it simply is, and between it and every instrument that has ever tried to read it, a vast and very ordinary darkness stretches. Ordinary, in the sense that interstellar space is ordinary, empty and cold, and crossed by light that takes years or centuries or millennia to arrive. The neutron star sits in that darkness as it has always sat, compact and impossibly dense and very quiet, and the only language it speaks outward is the language of its pulses and its heat and the very slow, very faint trembling of the space-time it curves around itself. What lives at the center remains, for now, an open question in the oldest and quietest sense. Not a problem demanding an answer, but a depth that has not yet been reached, a part of the physical world that exists with complete indifference to whether it is understood. The calculations will improve, the observations will sharpen, and the center of the neutron star will continue to hold whatever it holds in the cold and the dark and the extraordinary density that no name yet fully describes. While the long, slow work of understanding, it continues at the surface of a small planet many light years away, patient and incremental and very far from done. The crust turns overhead. The superfluid breathes its quantized breath, and somewhere in the deep interior, below the pasta layer, below the crystalline lattice, below the neutron drip point, where the free particles first begin to flow, the most uncertain matter in the known universe sits in silence, unchanged and unwitnessed. In the dark at the center of a city-sized star that has been keeping its secret since before the first human ever looked up at the sky and asked what the lights were made of. In a small room in Cambridge, in the autumn of 1967, a young woman sat at a long table covered in paper. The paper was chart recording, thin rolls of it, dozens of feet in total, printed with the faint ink traces of a radio telescope scanning the sky. Her name was Jocelyn Bell, and her work that morning, as on most mornings, was to read the squiggles, to look at the faint oscillations in the ink and decide which ones were from radio sources in the sky and which ones were from television transmitters, passing cars, or the general interference that a radio telescope picks up from a world not designed to stay quiet. It was painstaking work, done by eye, done by hand, done in the patient way that detection most often happens, not in a flash, but in the slow accumulation of careful looking. The telescope she was working with was not what the word telescope usually suggests. There was no dome. There was no eyepiece. It was a field roughly the size of 57 tennis courts, filled with wooden posts and wires strung between them, 4.5 acres of wire and timber laid out across the flat Cambridgeshire countryside to catch radio waves rather than light. Her supervisor, Anthony Hewish, had designed it. She had helped to build it. One trace on one roll of paper, that autumn, showed something that did not look like television interference. It was too regular. It pulsed, a brief, sharp burst of radio energy arriving at a fixed interval, repeating with a steadiness that earthly sources do not typically maintain. It came from a fixed point in the sky, which meant it moved with the stars. She flagged it. She returned to it. On faster chart recordings, she could see the pulses clearly, each one separated from the next by 1.3373 seconds, arriving with a precision that was, at that moment, unlike anything a natural source in space had been known to produce. The signal was initially called LGM-1. The letters stood for Little Green Men. It was not a serious proposal, but it was the kind of notation that captures, briefly and honestly, the genuine uncertainty of a moment before explanation arrives. The signal was so regular, so clock-like, that for a short time the possibility of an artificial origin was not immediately ruled out. Bell herself found a second source soon after, then a third and a fourth, each with its own precise period. Whatever these objects were, there were many of them scattered across the sky. Nature, it seemed, had found a way to build a clock. What nature had built was a neutron star, rotating, a star perhaps 20 kilometers across, carrying the mass of more than the sun, spinning tens or hundreds of times per minute, its powerful magnetic field misaligned from its rotational axis so that two narrow beams of radio emission swept outward through space with every turn. From a distance, the beams swept past like the beam of a lighthouse, visible once per rotation, then dark, then visible again, arriving at a distant radio telescope as a pulse, arriving with each repetition with the same interval to within a few millionths of a second. The Nobel Prize in Physics was awarded for this discovery in 1974. It went to Hewish, Bell's supervisor, and to Martin Ryle, who had led the development of radio astronomy techniques at Cambridge. Bell's own role, identifying the signal by hand in a sea of paper, and interference, flagging it, returning to it, finding the others, was not recognized by the committee. The exclusion was noted and debated and has not been forgotten. She continued working. Decades later, she would receive many of the honors that the Nobel had withheld, and the community's view of what had been done in that paper-covered room hardened, slowly, into something like consensus that she had found one of the most significant objects in the history of physics in the most careful and ordinary way imaginable. A pulsar, as these objects came to be called, is in some sense the simplest kind of neutron star to observe, because its rotation does the announcing. Somewhere in the galaxy, a neutron star is spinning in empty space. Its magnetic field extends outward from two poles and does not align with the axis around which it turns, the way Earth's magnetic poles do not align exactly with its geographic poles. Though in a neutron star, this misalignment can be large, and the consequences are extreme. The magnetic poles drive particle acceleration. Along each pole, electrons and positrons are flung outward at close to the speed of light, spiraling along field lines and emitting radiation in a narrow cone. Two cones of light sweeping around and around with every rotation of the star. From far away, if one of those cones passes across the line of sight, a pulse arrives, then silence, then another pulse, when the star has turned far enough to bring the beam back. The interval between pulses is the rotation period of the star, a number that can be measured to extraordinary precision. A pulsar with a period of 1 second is completing one full rotation every second. A pulsar with a period of a few milliseconds is rotating hundreds of times each second. The range spans many orders of magnitude, from pulsars that take several seconds per rotation, down to pulsars that spin so fast the mind needs a moment to follow the arithmetic. The pulse period does not stay perfectly constant. It lengthens slowly over time. Each rotation costs the star a small amount of energy, carried away by the outgoing radiation and by a wind of particles streaming outward from the magnetic poles. The star slows, barely, with every turn. From the measured rate at which the period lengthens, it is possible to calculate how much energy the star is losing, how strong its magnetic field likely is, and how long ago, if the star began spinning rapidly at birth, it formed. The slowing is tiny. A pulsar's period might lengthen by a fraction of a microsecond per year. Over centuries, it adds up. Pulsars age, the way all rotating things age, when friction or radiation is drawing off their spin, and the age written into their slowdown rate is one of the first things an astronomer reads when a new one is found. But there are pulsars that spin far faster than a young neutron star naturally should. Some complete several hundred rotations per second. The fastest confirmed example manages 716 rotations every second. A city-sized object carrying more mass than the Sun, completing 716 full turns in the time a human heartbeat takes to begin. These are called millisecond pulsars, and the way they come to spin so fast is not through birth, but through long patience. A millisecond pulsar is, in most cases, an old neutron star, one that formed hundreds of millions or even billions of years ago and has been slowing down gradually ever since. What changed it was a companion. In a binary system where the neutron star orbits close to another star, the neutron star's gravity can pull material from its companion, gas streaming across the space between them, spiraling inward, forming a disk of hot accreting matter, and eventually falling onto the neutron star's surface. Every particle of that infalling matter carries angular momentum, and angular momentum is not lost easily. It transfers to the neutron star. Over billions of years, across an incomprehensible number of infalling particles, the transfer accumulates. The star spins faster and faster and faster, recycled in the language of the field, from an elderly, slowly turning remnant into something that completes hundreds of revolutions per second. When the companion star eventually exhausts itself, when it has given up enough mass to fall quiet, or collapses into a white dwarf, or drifts away, the accretion stops. The millisecond pulsar is left alone, spinning at its new rapid rate, its magnetic field weakened by the same long process that spun it up, its period stable and almost impossibly steady. These recycled pulsars cool and darken over billions more years, but their rotation persists, and their pulsars continue to arrive, steady as the ticking of the best clock humanity has made, and in many cases, steadier. The steadiness of a millisecond pulsar is one of the most useful properties in observational astronomy. A pulse from a millisecond pulsar arrives at Earth with a predictability accurate to within a few microseconds over decades. The neutron star's enormous mass, rotating continuously, acts as a kind of flywheel, a massive spinning system whose rotation resists disturbance. Small variations in the arrival times of pulsars carry real information. A slight drift that repeats on a regular schedule can indicate the presence of a companion body tugging gravitationally on the pulsar as they orbit each other. Even a body far smaller than a star can be detected this way. The first planets ever confirmed outside our solar system were found not by watching a star dim as a planet passed in front of it, but by listening to a pulsar's timing. 3 small worlds orbiting a neutron star in the constellation Virgo, their presence announced by the tiny rhythmic wobble they imposed on the pulsar's otherwise perfect clock. Timing a pulsar precisely enough over long periods reveals subtleties beyond the presence of planets. A pulse of radio waves traveling through the interstellar medium is slightly slowed and dispersed by the thin plasma between the stars, higher frequencies arriving a fraction earlier than lower frequencies. The pulse spread in time by the column of electrons it passed through on its way to the telescope. The amount of this dispersal depends on how much electron-dense plasma the signal traversed. It is a measure of distance, of the density of interstellar space, of the plasma environment the signal moved through. Pulsars have become tools not only for measuring themselves, but for probing the structure of the galaxy their signals cross. They have become tools for something still more fundamental. Along a stretch of space, dozens of millisecond pulsars tick away like clocks placed at irregular intervals across the galaxy. each one monitored by radio telescopes over months and years. If something passes through the space between them, something that warps spacetime itself, the precise arrival times of pulses from different pulsars will be affected in correlated ways. Each clock will be shifted slightly, but in a pattern that reflects the passage of a wave through space rather than any individual disturbance. This is the principle behind pulsar timing arrays, coordinated networks of radio observatories, each monitoring a collection of the steadiest millisecond pulsars, all working together to detect the faintest ripples in spacetime at frequencies far lower than any earthly detector can reach. The waves such an array can detect are not the sharp, brief chirps from colliding black holes and neutron stars that swept past the ground-based detectors. They are slow, deep undulations, waves so long that a single wavelength might span light years, with periods of years to decades, generated by populations of massive black hole pairs at the centers of distant galaxies, spiraling together over millions of years. In 2023, several pulsar timing collaborations reported evidence consistent with a low-frequency gravitational wave background, a faint hum in the fabric of space, distributed across the whole sky, and detectable only because dozens of spinning neutron stars had been ticking faithfully and precisely for long enough that the pattern emerged from the noise. What was built to observe individual stellar remnants had become, over decades of accumulated data, a gravitational wave observatory the size of the galaxy. A young pulsar, one newly born from a stellar collapse, does not have the stability of a recycled millisecond pulsar. It is faster, in many cases, born spinning rapidly from the angular momentum compressed into it during the collapse, but also more variable, more energetic, and attended by a structure that a millisecond pulsar no longer maintains. The Crab pulsar spins 33 times per second. It was born when a massive star collapsed in an explosion that left a bright scar in the sky, observed and recorded by Chinese astronomers in 1054 CE as a new star visible in daylight for weeks. The remnant of that explosion is visible in any modest telescope today, a cloud of glowing filaments roughly 11 light-years across, tattered and complex, threaded with structure at every scale, the Crab Nebula. At the center of the nebula, the pulsar turns. It is losing rotational energy at a rate of approximately 5 times 10 to the 31st watts, more than 100,000 times the total power output of the sun, all of it drawn from the slowing of a 10-kilometer object spinning 33 times a second. That energy does not simply disappear, it flows outward into the surrounding nebula as a wind. The pulsar wind is not material in any ordinary sense. It is a continuous outpouring of charged particles, electrons and positrons, accelerated to close to the speed of light by the rotating magnetic field. These particles carry the energy away from the pulsar and inject it into the surrounding cloud of gas. Where the wind meets the slower, denser nebular material, there is a termination shock, a boundary where the wind abruptly slows and its particles are forced into the curved paths that cause them to radiate. The radiation they emit is synchrotron radiation, the light produced when a charged particle, moving at high speed, is bent by a magnetic field. It glows across a wide range of frequencies, from radio waves through visible light into X-rays. The result is what astronomers call a pulsar wind nebula. Not simply the shell of gas expelled in the explosion, but an inner region continuously lit by the ongoing energy output of the central pulsar, sustained not by the heat of the original blast, but by the present rotation of the neutron star at the cloud's center. The Crab pulsar has been maintaining this glow for nearly 1,000 years. Observations of the nebula at X-ray wavelengths reveal rings and jets of high-energy particles emanating from the pulsar, structures generated by the geometry of the magnetic field and the outflowing wind, changing measurably on timescales of weeks as the complex interaction between the wind and the field evolves. The nebula is not static. It moves, flows, brightens, and dims in regions, responds to what the tiny object at its center is doing right now. The coincidence of observation that tied all of this together arrived in stages. The Crab Nebula had been known for centuries as an unusual diffuse object in the sky. Its connection to the 1054 historical supernova was established in the 20th century by matching its position and its expansion rate, running the observed motion backward in time until the outward moving filaments converged on a point of origin roughly 900 years ago. A radio source at the nebula's center was identified. An X-ray source was identified. Then, in 1968, a radio pulsar was discovered at the nebula's center, with a period matching the expected spin rate of a young neutron star. The three pieces resolved into one object and one story. A massive star died, its core compressed into a spinning neutron star, and that neutron star has been powering the nebula's glow ever since. The same identification, made for the Crab and then for other supernova remnants hosting central pulsars, established the connection between stellar collapse and the lighthouse objects Bell had discovered. Not all neutron stars produce observable pulsars. The beam may not sweep across Earth, or the star may have slowed below the threshold of detectable emission, but pulsars, wherever they are found, are neutron stars. The lighthouse is the same object as the crushed stellar remnant, seen from a particular angle at a particular moment in its long cooling and slowing. There are pulsars that do not behave steadily. Alongside the slow, predictable lengthening of a pulsar's period, some pulsars exhibit sudden, brief increases in their rotation rate, moments when they spin fractionally faster than they were spinning before. These events are called glitches. They are abrupt. A pulsar that has been ticking with perfect regularity for months or years abruptly shows its pulses arriving slightly early, as if the star has momentarily spun up and then relaxes slowly back toward its previous rate over days or weeks. The Vela pulsar, a young neutron star in the southern sky, spinning roughly 11 times per second, glitches more dramatically and more frequently than most, its rotation rate jumping by a few parts in a million in an event that takes at most a minute. What happens inside the star to cause a glitch is not directly visible. The best current picture involves the neutron superfluid believed to exist in the star's interior. Deep beneath the crust, neutrons in the interior are thought to exist in a quantum mechanical state in which pairs of them flow without friction, a superfluid spinning inside the star as the crust spins above it. When a superfluid rotates, it does not rotate as a rigid body does. Instead, the rotation is carried by a lattice of thin, thread-like structures called quantized vortices, each one a tiny, rapidly rotating tube through which the superfluid circulates, and around which the superfluid is otherwise still. The entire rotation of the superfluid interior is encoded in the number and arrangement of these vortex threads. As the neutron star's crust slows down, pulled down by the outward radiation and particle wind, the superfluid beneath it does not immediately follow. The vortices interacting with the crystalline structure of the inner crust tend to be pinned in place rather than free to migrate outward, as they would need to in order to carry away angular momentum. The superfluid continues spinning at its previous rate, while the crust slows. A difference in rotation rate builds up between the interior superfluid and the solid crust above it, a kind of stored angular momentum, an accumulated discrepancy that cannot persist indefinitely. When enough vortices suddenly unpin simultaneously, when whatever holds them in place gives way, the stored angular momentum transfers suddenly from the interior to the crust. The crust spins up. The pulsar's period shortens. From far away, timing the pulses, an astronomer sees the pulsar arrive early and knows that something has shifted in the interior of a star no instrument can directly see. The glitch is the only signal. The superfluid is the explanation that fits it. The inference is strong enough to be broadly accepted, and indirect enough that the details remain uncertain. Glitches are one of the few observational windows into the interior of a neutron star that do not require looking at the star's surface or waiting for a merger. They carry information about how much of the star's moment of inertia resides in the superfluid interior relative to the crust, about the coupling between those two components, and about the properties of the vortex-crust interaction. None of that information arrives cleanly. It arrives wrapped in uncertainty, dependent on models, dependent on equations of state that remain unsettled. But it arrives, in the only form it can, as a tiny deviation in the arrival time of a radio pulse, felt across hundreds of light years by an antenna aimed at the right patch of sky. The radio pulsar is the most familiar kind of neutron star, but it is not the only kind. At shorter wavelengths, in X-rays, other neutron stars announce themselves by a different method. Some are heated by accretion, material falling from a companion star, converting its kinetic energy into X-rays as it strikes the surface. Others are young enough to be intrinsically hot, their surface temperatures still high enough to glow in X-ray light. A few are the most magnetically extreme objects in the universe, neutron stars whose fields are not the 10 to 12 Tesla, typical of an ordinary pulsar, but something closer to 10 to the power of 10 Tesla, fields so intense that they can fracture the neutron star's own crust, break through the surface, and release bursts of energy so powerful they have been measured across the width of the galaxy. But the lighthouse, the radio pulsar, the rotating beam in the dark, is the form in which neutron stars were first understood, and it remains the form in which they are most precisely measured. The pulsar timing residual plot, a strip of data points stretching across years of observation, each point representing the measured arrival time of a pulse minus the predicted arrival time, is one of the most information-dense images in observational astronomy. When those points scatter randomly around zero, the pulsar is quiet, its interior undisturbed, its orbit empty. When they show a gentle curve, a planet or companion is tugging the star in its orbit. When they show a sudden step, something shifted inside. When they drift slowly away from zero across years and then return, a gravitational wave may have passed by. The precision required to read any of this is not the precision of ordinary clocks. It is the precision of atomic standards compared against each other over years, not propagated through models of the pulsar's position, its proper motion across the sky, the dispersion of its signal in the interstellar medium, the relativistic corrections needed because the telescope is on Earth, and Earth is moving around the Sun at 30 kilometers per second through curved spacetime. All of those effects are real, and all of them need to be subtracted before the residual. The part that is not accounted for by known physics can be examined for new signals. What is left after that subtraction, in the best-timed millisecond pulsars, is astonishing in its quietness. A residual that shows no trend, no drift, no systematic deviation from zero across years of data is itself a statement about the universe, that in the direction of this pulsar, over this period, nothing measurable distorted the space-time that the pulses crossed. The absence of signal is the signal. A pulsar timing array, monitoring dozens of pulsars simultaneously, is listening for correlations, pairs of pulsars where the residuals move together, in a pattern that would emerge if a long gravitational wave were gently stretching and compressing the space between the Earth and all of them at once. The correlations are subtle. They depend on the angular separation between pulsar pairs and the pattern they follow, called the Hellings-Downs curve. From the theoretical prediction made in 1983 is a specific signature that distinguishes a real gravitational wave background from any common noise source that might affect all telescopes on the ground. In 2023, 4 independent pulsar timing collaborations published results that collectively showed the statistical imprint of this pattern in their data. The correlations were present. The signal was consistent with a low-frequency gravitational wave background, most likely produced by a population of supermassive black hole pairs in the distant universe, objects each containing millions or billions of solar masses, bound in binary orbits that are slowly tightening over millions of years and will eventually produce the largest gravitational wave mergers the universe can generate. The neutron stars in those timing arrays were not involved in producing the waves. They were simply present, spinning steadily, generating the precision needed to feel the background vibration in the structure of space itself. And what they felt, across years of patient observation, was the gravitational aftermath of a process happening in galaxies hundreds of millions of light years away. A radio telescope in the mountains of Puerto Rico, until its structure collapsed in 2020, had been one of the great instruments used for this work. The Arecibo Observatory, with its 300-meter dish, could time pulsars with a sensitivity that still influences the datasets used today, even now that the telescope is gone. The Green Bank Telescope in West Virginia continues. The Parkes Observatory in Australia continues. The Meerkat Array in South Africa continues. FAST, the 500-meter aperture spherical telescope in China, the largest single-dish radio telescope ever built, continues and is extending the precision further. More pulsars, longer baselines, more years of accumulated timing. The array grows, and the sensitivity of the measurement it embodies deepens with every additional year of clean data. Jocelyn Bell, now Jocelyn Bell Burnell, has seen all of this unfold from the science she was 24 years old when she did. The field she found has grown into something she could not have anticipated when she sat with her paper rolls and her careful eye looking for anything that did not fit the noise. In 2018, she was awarded the Breakthrough Prize in Fundamental Physics, worth $3 million, which she donated in full to fund scholarships for students from underrepresented groups in physics. She has said that what happened to her, being overlooked by one prize while her male supervisor received it, likely turned her into a better astronomer because she stopped expecting reward and focused on the work. Whether that is accurate or a generous reading of something harder than it sounds, the work she did that autumn has not faded. The signal she found, CP19, 1.3373 seconds between pulses, arriving from a fixed point in the sky, was the first confirmed radio pulsar. It has been observed continuously since its discovery. Its period now is slightly longer than it was in 1967, as the star has continued to slow. In 1 billion years, if nothing intervenes, it will have slowed below the threshold of radio emission and gone quiet. But it will still be there, a cold, dense, dark sphere, roughly 10 kilometers across, drifting alone through whatever region of the galaxy it has reached by then, carrying in its diminished rotation the angular momentum accumulated when a star many times the mass of the Sun collapsed inward in less than a second and left behind, of all things, a clock. The lighthouse is not separate from the dark. It exists within the dark, turning inside it, and the dark is most of what is there. Between each pulse and the next, the beam has swept around and pointed somewhere else, and from the Earth, the sky at that position shows nothing, no visible star, no optical glow, just the quiet radio sky. Then the pulse comes again, on time, a second later, or 33 times a second, or 716 times a second, arriving after traveling hundreds or thousands of light years across the thin plasma of the galaxy, carrying in its precise arrival time the record of every gas cloud it passed through, every curve in space-time along its path, every shift in the pulsar's own interior since the last pulse left. A millisecond pulsar in a distant part of the galaxy has been doing this since before the solar system formed, its companion long since consumed and gone, its magnetic field weakened to a fraction of what it was at birth, its surface dark and cold and invisible to any optical telescope. It spins on 300 rotations per second, 500, 700, announcing itself in radio to any receiver pointed at the right spot in the sky. The announcement carries nothing dramatic. It is not a warning. It carries no message except the one intrinsic to its nature, that it is there, that it is still turning, and that the time between one pulse and the next is as close to constant as anything the natural world produces. That constancy, spread across dozens of pulsars, aimed in dozens of directions, measured across decades, becomes something larger than any individual clock. It becomes a network, a net of steady ticking cast across the volume of the galaxy, sensitive to the faintest distortions in the medium it occupies. The gravitational waves from colliding black holes in distant galaxies pass through that net, leaving their trace in the correlated timing of clocks they never touched. The net catches them anyway, in the accumulated patience of the measurement, in the residuals computed after everything else has been accounted for, in the slow and careful way that physics most reliably learns anything. The same room in Cambridge still exists. The field where the telescope stood has long since been repurposed, its wooden posts and stretched wire gone. The chart recordings are archived. The specific squiggle on the specific roll of paper that corresponded to the signal bell, called LGM1, has been photographed and described, and the photograph reproduced in 100 textbooks. The original signal arrived from a star perhaps 2,000 light-years away, and that star is still rotating, slightly slower than it was in 1967, and the beam is still sweeping around. And if a radio telescope with a wide enough field and a sensitive enough receiver were pointed at that part of the sky right now, the pulse would come, 1.3373 seconds, and then the next, and then the next, as steady and as quiet as the dark in which it turns. There is something that settles in that image, considered slowly, not the violence of the star's birth, not the compression of matter beyond any ordinary limit, not the rotating field in the particle wind and the expanding nebula with its synchrotron glow. All of that is real, all of it underlies the pulse. But the pulse itself, arriving on time, having crossed thousands of light years of interstellar space, is quiet. It asks nothing. It does not require understanding to continue. It would have arrived before there were radio telescopes. It arrived when the only creatures listening were the distant ancestors of the people who would eventually build the instruments to hear it. It will continue arriving long after those instruments are gone, if anything is there to receive it or not, because the star at its source has no knowledge of being observed and no need of an audience to keep turning. The pulsar timing arrays listen on, adding another month of data, another year, refining the residuals, looking for the pattern in the noise that would confirm or deepen what the 2023 results suggested. The telescopes are large and cold and pointed at many parts of the sky at once. The millisecond pulsars they are monitoring are scattered across thousands of light years in every direction, each one a spinning remnant of a star that died long before the solar system existed, each one ticking at its own steady rate. And between all of them and the telescopes, the gravitational wave background hums at a frequency too low to see or feel, only felt, if at all, in the slow accumulation of data that measures the space between one pulse and the next and asks very quietly whether anything out there has been stretching and compressing the distance that the signal had to cross. The answer coming back from the data, slowly, over years, is beginning to sound like yes. And the thing that made the measurement possible is a woman reading chart paper by hand in 1967 and a star 2,000 light years away that collapsed into 10 kilometers of neutron matter and began immediately to spin. In the final seconds before two stars collide, the space between them is no longer empty. Space-time itself is moving. It bends and stretches in great slow ripples that travel outward at the speed of light, carrying with them the story of what is about to happen. Two objects, each heavier than the sun, their separation now measured in hundreds of kilometers, closing at tens of thousands of kilometers per second. The in-spiral has been going on for hundreds of millions of years. The last second lasts less than a breath. They have been circling each other since long before the Earth existed, slowly, patiently, over geological time, and then over stellar time, their orbit tightening as each revolution shed a little energy into gravitational waves, the two stars spiraling inward without ever touching, the gap between them diminishing by amounts too small to measure in any given year, and yet inexorable across the long dark. And now the gap is gone. The collision is not an impact in the ordinary sense. It is a merging, a tidal unraveling, a sudden catastrophic pooling of two compact objects whose combined mass tests the upper limit of what neutron star matter can support against gravity. The ejecta that flies outward in the first milliseconds moves at a fraction of the speed of light. It is extraordinarily dense, extraordinarily rich in free neutrons, and it is already doing something no supernova remnant can do, no stellar wind, no quiet accretion. It is building atoms that the universe could not make before. 130 million light years away, a radio telescope on Earth caught nothing of this. The light would not arrive for another 130 million years. But something else arrived almost instantly. Gravitational waves travel at the speed of light, and the waves from this collision reached detectors on Earth on the 17th of August, 2017. Two instruments, one in Louisiana and one in Washington State, felt the signal as a slow chirp rising over 100 seconds, a frequency climbing from the low registers of a large pipe organ into something higher, tighter, faster, until the merger itself silenced the signal in a final burst. The signal was called GW 170817. It lasted about as long as it takes to breathe slowly in and out twice. What the signal encoded in its shape was the mass of each star, the way the tidal forces of each star had slightly distorted the shape of the other in the last moments before contact, and from that distortion, something about the stiffness of neutron star matter how resistant it was to compression, how the pressure inside it scaled with density. The waveform was a message written in the geometry of space-time itself about the interior of the densest stars. And physicists read it. The signal arrived at the detectors in Louisiana and Washington state 17 thousandths of a second apart, a tiny difference that reflected the slightly different distances from the galaxy in question to each detector's location on Earth. From those two measurements alone, combined with the signal's shape, the direction of the source could be narrowed to a region of sky, not precisely, but enough for telescopes to look. They looked, and about 1.5 seconds after the gravitational wave signal ended, a telescope in orbit around Earth detected a short burst of gamma rays from the same general direction in the sky. It was brief, it was faint, it was unmistakable. For decades, astronomers had speculated that when two neutron stars merged, the collision would produce a short gamma ray burst, a flash of the most energetic radiation in the known universe, visible across billions of light years, lasting a second or two. This was the first time anyone had seen a gravitational wave from a neutron star merger and a gamma ray burst from the same event at the same moment. Theory and observation arrived together. Within 11 hours, telescopes on the ground found it, a small brightening in the outskirts of an ordinary elliptical galaxy in the constellation Hydra, a point of blue-white light where no point of light had been before. It grew, and then it faded. Over 2 weeks it reddened, as if the color of whatever was burning there was shifting from the blue end of the spectrum toward the infrared, the light darkening and extending into wavelengths the human eye cannot see. This was the kilonova. The name is precise, kilo, for 1,000 times the brightness of an ordinary nova. But the true significance of what was happening inside that fading, reddening glow was not in its brightness. It was in the atoms being assembled in the cooling ejecta cloud, invisible inside the light. The cloud moving away from the merger site was neutron-rich in a way that no other astrophysical environment could match. Free neutrons saturated it. Seed nuclei, the nuclei of lighter elements already present in the two stars, were being struck by these free neutrons thousands of times before they had any chance to decay, each capture adding mass to the nucleus, driving it into configurations far beyond the stable elements, beyond the heaviest atoms that stars alone can forge, into the domain of the lanthanides, and beyond, into gold and platinum and uranium and the full suite of the heaviest naturally occurring elements in the periodic table. This process, the rapid capture of neutrons, takes place on timescales of milliseconds. It builds, in those milliseconds, nuclei that took billions of years to be understood. The spectroscopic light from AT 2017 Graph O, the formal designation of the kilonova, contained the signature of strontium. The reddening of the light over days was consistent with the radioactive decay of freshly synthesized lanthanide elements, heavy atoms whose electrons scattered the bluer wavelengths and let the redder ones through, like a cloud of extraordinary matter slowly becoming transparent. The modeling of the light curve suggested that somewhere between 1/100th and 5/100ths of a solar mass of neutron-rich material had been ejected, moving at between 1/10th and 3/10ths of the speed of light. Inside that material, enough gold to make roughly 10 Earths had been forged in a matter of milliseconds. The number is difficult to hold still. 10 Earths, the mass of 10 entire planets, assembled from iron and oxygen and silicon, all of it converted instead into gold, a single element, freshly made, radioactively warm, expanding outward through a small galaxy of no particular distinction 130 million light-years from here. And yet the number, once held quietly, begins to feel less like an excess and more like an accounting. The universe has been running this process for a very long time. Galaxies contain hundreds of billions of stars, and among them are binary systems of neutron stars that spiral together over hundreds of millions of years before merging. Each merger produces a kilonova. Each kilonova seeds the surrounding interstellar medium with heavy elements. The gas and dust of a galaxy, over billions of years of star formation and stellar death and merger events, accumulates these elements slowly, a gram here, a kilogram there, spread across volumes of space so vast that the enrichment is almost imperceptible in any single region. But the enrichment is real, and it is cumulative, and it is measurable in the spectral lines of distant stars, whose atmospheres were assembled from gas that had already passed through the aftermath of mergers long ago. The gold in the Earth's crust was not made here. The sun could not make it. No single star could. Gold sits too far from iron on the chart of nuclear binding energies to be reached by the slow processes of stellar nucleosynthesis. It required free neutrons in extraordinary abundance, extreme neutron richness, timescales fast enough to bypass nuclear stability. It required the conditions that exist in the entire known universe in only a small number of settings, and the most important of those settings is the collision of two neutron stars. The gold in the Earth arrived with the planet, gathered from the primordial dust cloud that also built the sun, which was itself assembled from gas that had been enriched over billions of years by earlier generations of stellar deaths and mergers. The Earth is old, 4.5 billion years, rounding modestly, and the universe is nearly 3 times older than that. In the time between the Big Bang and the formation of the Sun, neutron star mergers were already running, already enriching the interstellar medium, already depositing the raw material for all the gold and platinum and uranium and rare earth elements that the solar system would later collect. There is a quiet lineage here. The gold does not remember where it came from. The atoms that make up a gold ring are simply atoms, carrying no history in their structure that any instrument has yet learned to read. But the history is there in the abundances, in the relative proportions of heavy elements in the solar system's composition, which match in their broad outline what the models of neutron star merger nucleosynthesis predict. The match is not perfect, and the field is still working through the details. It may be that core collapse supernovae contribute a portion of the R process inventory too, but the overall picture is clear enough to say with confidence the heaviest elements in the periodic table were forged primarily in the collision of neutron stars. Platinum rests in laboratories, in catalytic converters, in the electrodes of instruments designed to measure other things. Uranium powers reactors and sits inert in ore deposits in the ground. These materials feel dense and old in the hand. They are both. The density is nuclear, an echo of the interior conditions in which these atoms were made, inside a cloud of ejecta launched by the collision of objects denser than any other matter in the universe. The age is real. Most of these atoms are billions of years old, having traveled from their formation site through the interstellar medium into the nascent solar system, into the geology of the early Earth, through billions of years of geological cycling, and finally into whatever form they occupy today. The weight of a gold ring is in one sense the weight of a neutron star merger, diluted by time and space into a small familiar object. There is another boundary that the merger event approaches, and it is worth approaching slowly. The two neutron stars of GW 170817 each carried a mass somewhat less than 2 solar masses. Their combined mass was roughly 2.5 solar masses, possibly more. When they collided, the product, whatever briefly existed at the center of the kilonova, faced a question that no equation has yet answered with certainty. Was the combined mass too great for neutron star matter to support? A neutron star can only be so massive. Beyond a certain threshold, no pressure, not neutron degeneracy pressure, not the strong nuclear force, not any known mechanism, can resist gravity. The object collapses to a black hole. The precise location of that threshold is not known because it depends on the equation of state of dense nuclear matter, which is still being constrained by observations. Current estimates place it somewhere between roughly 2 and 3 solar masses, with the most careful analyses suggesting the upper limit may be around 2.5 solar masses, perhaps a little more. The product of GW170817 may have briefly exceeded this limit. If it did, it collapsed within milliseconds to a black hole, its neutron star existence lasting less time than it took the gamma-ray burst to form. If it did not, if the remnant was massive enough to be supported only by rapid rotation, an object called a hypermassive neutron star, it may have persisted for seconds or longer before collapsing. The gravitational wave signal from the merger itself does not tell us which occurred, because the frequencies involved in the post-merger oscillation, above 1,000 cycles per second, lie at the edge of what current detectors can hear. Future instruments, more sensitive in the kilohertz range, will listen for this signal in the next generation of merger events. It is one of the cleanest ways to learn what happens to matter at the highest densities, and whether the product of a collision becomes another neutron star, a black hole, or something in between. There is something fitting in that uncertainty. The merger of two neutron stars is the most consequential event in neutron star physics. The event that built the heavy elements, confirmed the source of short gamma-ray bursts, opened the era of gravitational wave astronomy, and narrowed the equation of state in ways decades of pulsar observations had not managed. And yet even this event, measured with extraordinary precision by instruments on 3 continents, leaves the interior physics unresolved. The densest matter in the universe declines to be fully read. The galaxy NGC 4993, where GW170817 occurred, is an elliptical galaxy, an older, redder structure without the spiral arms that carry active star formation. It is a quiet place as galaxies go, its stellar population aging and cooling. The neutron star binary that merged there had been circling each other long enough for the galaxy itself to have changed shape and composition around them. Its spiral structure, if it ever had one, long since dissolved into the smooth ellipsoidal distribution that elliptical galaxies eventually settle into. The merger was the most violent event that galaxy had produced in perhaps millions of years. The kilonova faded over 2 weeks, and then the outskirts of NGC 4993 were dark again. 130 million light-years is a distance that becomes quietly incomprehensible only when it is stepped through slowly. Light travels about 6 trillion miles in a year. 130 million years of light travel time. The event occurred during the Cretaceous period, roughly, if one uses Earth's geological clock as a reference, though of course the Earth and its geological periods meant nothing to the galaxy in question. The light of the explosion had been traveling for longer than dinosaurs existed. It arrived in 2017 because the expansion of the universe placed that galaxy at that distance when the light set out, and because the speed of light is what it is, and because nothing intervened. It arrived and was recorded, and will be analyzed for decades. The atoms forged in that event will not arrive. They are dispersed into the interstellar medium of NGC 4993, too distant and too diffuse to ever reach the solar system. But atoms forged in events like it, in our own galaxy, in the Milky Way's own history of neutron star mergers over 10 billion years, are here already. They are in the crust of the Earth, in the oceans, in the continental rock. They are in every living thing. Gold is not alive. It does not participate in biochemistry in any significant way. But the same process that made gold also made elements that do, rare earths and heavier metals that ended up in catalysts and industrial processes, and more distantly, in the trace elements that biological systems have incorporated over evolutionary time. The R process enriched the universe with atoms, and life, which will use whatever is available, has used some of them. There is a particular stillness in this. Not the stillness of emptiness, but the stillness of completion. A long chain of events that began in the formation of massive stars, ran through their depths and the remnants they left behind, accumulated across billions of years of binary evolution and orbital decay, and ended in a collision that lasted less than a second, releasing in that second more energy than the sun will produce in 10 billion years, and in doing so depositing into the surrounding interstellar medium atoms that would become, among other things, the material world that a species on a small planet in a different galaxy would one day weigh and measure and trade. The gravitational waves of GW 170817 passed through the Earth and continued outward. They are still moving, at the speed of light, in an expanding sphere, now about 130 million light-years in radius. By the time those waves reach the edge of that sphere, they will be so attenuated as to be unmeasurable by any instrument. They will continue, attenuating further, forever. A record of the event will propagate outward through the universe for as long as the universe exists to propagate through, growing too faint to read long before the end, but never quite stopping. The kilonova faded on the time scale of weeks. The gamma ray burst lasted about 2 seconds. The gravitational wave chirp lasted about 100 seconds. The merger itself, the moment of contact, lasted milliseconds. The inspiral that preceded it lasted hundreds of millions of years. And the heavy elements produced in that single collision will persist, barring some catastrophic process, for timescales that exceed the current age of the universe many times over. Gold does not decay. The heavy stable isotopes forged in a neutron star merger sit at the bottom of their respective nuclear valleys and change into nothing. An atom of gold made in a kilonova before the Earth existed will remain an atom of gold long after the Earth is gone. This is the longest persistence that ordinary matter achieves. The atoms continue, stars form and die, planets form and are absorbed by aging stars, galaxies evolve, and their oldest stars cool and dim, but the atoms, cycling through gas clouds and planets and living things and back into gas clouds, persist through all of it. The gold is patient in a way nothing alive can match. It waits in whatever form it finds itself, ring or ore or dissolved trace in seawater, without any quality that could be called waiting, simply persisting, the longest-lived artifact of the most extreme physics the universe produces. The neutron star itself, the remnant that preceded the merger, is no longer a neutron star. It is gone, absorbed into whatever the merger created, perhaps a black hole, collapsing inward in the moments after contact, leaving behind a gravitational absence in the outskirts of NGC 4993, dark and still, and radiating nothing but the faint Hawking radiation that theory predicts and no instrument has yet confirmed, across a region of space that holds no memory of the stars that were there before. The Crab Nebula is still visible. It sits in the constellation Taurus, expanding at about 1,500 kilometers per second, its tattered filaments of glowing gas stretching now across roughly 11 light years, a distance that light takes 11 years to cross, filled with material that was once the outer layers of a massive star. The star died nearly 1,000 years ago. Chinese court astronomers recorded the new bright point in the sky in 1054 of the Common Era, visible in daylight for 23 days. The Crab pulsar at its center, the neutron star that the core collapse left behind, spins 30 times per second and slows, measurably over years, its rotational energy feeding the nebula's continued glow. The nebula will continue to expand. In tens of thousands of years, it will have diluted into the surrounding interstellar medium, indistinguishable from the gas between stars, and the pulsar will still be there, spinning somewhat more slowly, cooling, radiating into a galaxy that has moved on from the explosion that made it. A neutron star in a binary system, in the right conditions, will spiral toward its companion over millions of years, shedding gravitational energy in waves too faint for any instrument to have detected yet from that particular pair, its orbit shrinking by amounts too small to notice in a human lifetime, but accumulating across geological time. And one day, a day hundreds of millions of years from now, or perhaps already past, in some part of the galaxy not yet observed, the separation will reach its limit, and what remains will merge, and a kilonova will briefly outshine the galaxy in which it occurs, and atoms will form that the universe had no other way to make. The process is running now in the Milky Way and in every galaxy beyond it. Neutron star binaries are tightening their orbits. The gravitational waves they emit are too faint to detect individually from this distance, but cumulatively, as a background hum of gravitational waves from all the binary systems in all the galaxies in the observable universe, they contribute to a gravitational wave background that sensitive pulsar timing arrays are beginning to detect, a faint signal encoded in the arrival times of radio pulses from millisecond pulsars scattered across the sky. The universe is full of pairs of objects falling slowly toward each other, broadcasting their infall in a language that space-time itself speaks. The listening instruments are now sensitive enough to hear it, just barely, as a kind of stochastic hum beneath the silence. The gold in the earth is not going anywhere, neither is the platinum in the laboratory, or the lanthanides in the electronics, or the uranium in the rock. They are as stable as atoms can be. They will outlast the planet that holds them when the sun expands in 5 billion years and the Earth's surface becomes uninhabitable. These atoms will still be atoms, cycling through the changed chemistry of whatever the Earth becomes, or scattered if the Earth is absorbed, drifting through the solar system's remaining material, eventually perhaps gathered by some future object, or dispersed permanently into interstellar space. And even in interstellar space, drifting free, they persist. An atom of gold in a gas cloud is an atom of gold. It has nowhere to be, and all the time in the universe to be there. Its nucleus, assembled in milliseconds in the neutron-rich ejecta of a collision, carries in its structure the same number of protons it was made with, the same tightly bound configuration of quarks, unchanged from the moment it formed. It does not age. It is not subject to the biological deterioration or the geological cycling that reshape everything else. It is simply there wherever there happens to be, waiting in the way that matter waits, without anticipation, without awareness, without end. There is something deeply restful in this. Not the rest of exhaustion, but the rest of completion. The chain of events that forged the heavy elements is not a tragedy and not a triumph. It is physics unfolding across scales and time scales that dwarf anything biological, producing as a side effect the full complexity of the periodic table, all of it available to whatever processes, stellar, planetary, biological, come later. The elements do not know they were made in the collision of neutron stars. They do not know anything, but the record is in them, in the isotopic ratios, in the relative abundances of the R process elements relative to lighter ones, in the way the pattern of heavy element enrichment in old stars tracks the history of merger events across galactic time. Cosmochemistry reads this record, imperfectly, with improving precision. The story of where each element came from is written in the composition of stars and planets, and each decade's better instruments and better models add another line to the reading. What the reading says, in its current form, is this: the universe made the lightest elements in its first few minutes, in the hot, dense plasma, after the Big Bang. Stars made the elements from carbon through iron over billions of years of nuclear fusion. And the elements heavier than iron, the ones that require neutron-rich, high-density, rapid capture conditions, were made primarily in the deaths and collisions of the densest stellar remnants, in events so brief and so violent that the gold produced in a single second of merger time would take the light of the colonova 2 weeks to cool and fade. The sun will not produce gold. It burns hydrogen now, quietly, and will burn helium when the hydrogen is gone. And when that too is exhausted, it will expand and cool and eventually shed its outer layers as a planetary nebula, leaving behind a white dwarf, a dense hot remnant made of carbon and oxygen, supported not by nuclear burning, but by the quantum mechanical resistance of electrons to compression. The white dwarf will cool over billions of years into darkness. It will not merge with anything unless a companion provides the conditions for it. It will simply cool. The heavier stars, the ones that end in core collapse, do produce R process elements in small quantities in the supernova ejecta. Some fraction of the heavy element inventory of the galaxy may have come from these events, but the detailed modeling of supernova nucleosynthesis suggests that core collapse supernovae on their own cannot account for the observed abundances of the heaviest elements. The merger of neutron stars is required. The observation of AT 2017 GFO, with its spectroscopic signatures and its light curve consistent with lanthanide production, confirmed this directly, and the field has not been the same since. There is a small galaxy called Reticulum 2, a dwarf satellite of the Milky Way. It has very few stars, fewer than 1,000 perhaps, and its stars are extremely metal poor, meaning they formed from gas that had been enriched by very few previous generations of stellar processing. Most of these stars have very low abundances of Rye process elements, but a handful of them are dramatically enriched in Rye process elements, gold, europium, barium, far beyond what a uniform distribution across the dwarf galaxy would predict. The explanation that fits best is that very early in the history of this dwarf galaxy, a single neutron star merger enriched a small region of it, and the stars that formed from that region carry the chemical signature of that one event, diluted only by the small amount of gas in their natal environment. Reticulum 2 is a kind of fossil record. Its unusual chemical composition is the preserved trace of a single neutron star merger that occurred before those stars were born. Its heavy elements spread through a volume of gas that then collapsed into a handful of stars that carry the Ara process signature to this day, billions of years later, in their photospheres, readable by spectrographs on telescopes on a different planet in a different galaxy. The merger that enriched reticulum, too, occurred before the Sun existed. The stars carrying its signature are among the oldest in the local group. Their gold was made before there was an Earth to hold gold. It has been in those stellar photospheres ever since, circling the center of the Milky Way, waiting in the way that atoms wait, patiently, without agenda, simply there. The two neutron stars of GW1 70817 began as massive stars in NGC 4993, long before the first human beings existed. They ran through their nuclear fuel, one after the other, in the usual way of massive stars, burning hydrogen, then helium, then heavier elements in successive shells, accumulating iron cores that could not burn, collapsing in seconds, driving shock waves outward that peeled their outer layers into space. Each left behind a neutron star, dense, spinning, magnetic, city-sized, and star-massed, cooling slowly in the outskirts of their host galaxy. By chance or by the dynamics of the binary system that initially held their progenitor stars, the two neutron star remnants remained bound to each other. They began their long spiral. Over hundreds of millions of years, they circled. The galaxy evolved around them. Stars formed and died. The interstellar medium cycled through cloud formation and star formation and stellar winds and supernova explosions. The two neutron stars continued their orbit, oblivious, not oblivious in the way a sleeping animal is oblivious, but oblivious in the way that objects without minds are oblivious, simply following the path that their mass and velocity and the curvature of space-time prescribed. When they finally met, it lasted less than a second. What they built in that second, the heavy atoms launched outward in the ejecta cloud, will last longer than any star. The universe is very old and very large and mostly very quiet. In the quietness, processes run at scales and timescales that no single observation captures completely. The spiraling of binary neutron stars, the slow enrichment of galactic gas, the accumulation of heavy elements in the dust clouds that become new solar systems, the gathering of those elements into planets, into rocks, into ocean water, into the mineral substrates from which life eventually draws what it needs. The kilonova fades, the gravitational waves disperse. The ejecta cloud expands and cools and eventually merges with the surrounding medium of NGC 4993, its atoms indistinguishable from all the other atoms in that galaxy, no longer moving faster than the local velocity dispersion, no longer hot, no longer radioactive, simply present, gold and platinum and strontium and dozens of other elements scattered across the outskirts of a galaxy that has already forgotten the violence that made them.